Hi everyone. In today's installment of Programming for Lovers, I'd like to do three things. I'd like to come back to Go and talk a little bit more about how Go implements arrays and slices, which we worked a little bit last time that we worked in Go. I'd like to also talk about strings, and I'd like to talk about maps as well. And I'd like to tie all this back into what we've done already with respect to finding frequent words in bacterial replication origins. I will leave the problem of finding the bacterial replication origins to you, since it's a problem that I can allow you to do, which we saw in the previous lecture reduced to finding a minimum position of a skew diagram. So I'd like to start with a little bit more about arrays in Go, and specifically slices, since this will allow us to deal with arrays of variable lengths. And I've created an arrays folder in our Go src directory, and I've got a main.go there in the arrays folder too. And so in this file, hopefully it's going to open, so in this file, I have copied over the prime finding algorithm that we had last time, Civ Veritasthenes, and this function takes an integer n, and it returns a slice of n+1 booleans, where the pth element of this array is true if p is prime, and it's going to be false otherwise. So got a couple of things going on here. Sorry, got some package installs going on behind the scenes. This is going to use a cross-off multiple subroutine. So how this function worked was it created a slice of booleans representing true or false, prime or not prime, and then we ranged over the array, set everything to prime other than 0, 1 at the start, and then we crossed off the multiples of each prime number that we saw. So we started at p equal 2, crossed off the multiples of 2, then we checked if prime array of 3 was true. It was. We crossed off the multiples of 3. Prime array of 4 was not true because it had already been crossed off when we crossed off the multiples of 2, and so on. And so in the end, we have this nice short function that calls one subroutine cross off multiples, and that is actually very visibly faster than the trivial algorithm for prime finding. So that's the algorithm that we had before. Now I'd like to say a little bit more on arrays and slices. So one motivating problem would be we would love to have a function called something like list primes that takes an integer n and that returns a slice of integers. And what does this do? This function should takes an integer n and returns a list of all prime numbers up to and including n. And so we would like to do something like set primes equal to make a slice of ints, and then have some value there, because in the end we're going to want to return the list of prime numbers that we find. So the issue here is that we would like to do this, and I think I have a low frame rate on the stream, so if that continues, let me know, and we'll reassess. But the problem here is that I have question marks here because I don't know how many prime numbers there are up to and including possibly n. There is actually a prime number theorem that will allow us to estimate this really well, but it doesn't tell the exact number. So what we learned about last time said that I currently would need to know the length of my slice in advance, but I don't know that yet, and so that will motivate kind of part 2 of this prime finding or discussion of arrays. So I'll hold off on this for now because we won't have everything that we need to do this, so I'm just going to comment it out, and I'm going to say a little bit more about arrays. So let's have a function called max, okay? And let's have this max function take some list that's a slice of integers, and let's have it return the maximum of this slice. So it should return an integer. And so we want to declare, say, a variable to be an integer, m, and in the end, that's what we're going to return. And it's very tempting to write this function where we declare m, we range over all the values in the list, and so we could say for I colon equals 0, I less than the length of the list, I plus plus, or whatever index variable that we want to use. And as a result, we are going to, after when we range, we're going to check, is it the case that list of I is indeed bigger than whatever the current maximum value that we have is, which I'm calling m. And if that's the case, I want to update m to be list of I. So at the end, I'm going to return m, and so I've ranged over the list, updating m if we find a bigger value. There's just one issue with this, which is that if, for example, everything in the list is negative, then there's still a maximum value of that list. So if everything is negative and the maximum is, say, negative 33, that's the biggest element in our array. And the problem here would be m would get declared, and so it would have the default value equal to 0. And it would never get updated because everything in the list is negative, so it's less than or equal to the value of m that we start. And we would return m, which would be equal to 0 if everything in the list is negative. So we would have a bug here in our program, in our function, where it would behave correctly for anything that contains a non-negative value in the list, but then for this separate case where everything is negative, we wouldn't get the result that we desired. So instead, we need to find a workaround. And the workaround that we're going to look at is to say, well, how can we fix this? We want to update m. We want to update m in two cases. We want to update m if it's the case that list of I is bigger than the current value of m. And we also want to do it if we're at the first value. So if we're either at the first value or the current value in the list is bigger than the biggest value that we found, then we're going to update m. And this will avoid the issue where if everything is negative, we won't ever update m, because if everything is negative, I'll hit I equals 0, and that's just the 0th item in my list, and I'll set m equal to that 0th item. Of course, we also should, if we're being completely precise, we should probably have an if length of list is equal to 0. So if there's nothing there, you could take a variety of approaches. It would be strange to call maximum of an empty list, and so maybe for our purposes here, we would flag that as an error. Okay. So that just shows how even for a simple function where we're taking the maximum of a collection of integers or an array of integers, we can still have issues where we need to check these little side or corner cases where we have an empty list or we have things that a list that has only negative values. Okay, so I introduced this problem because there's a nice shorthand. We're starting to see that ranging over a list is a very common thing that we would do, or ranging over a slice. And so as a result, this notation, I colon equal to 0, I less than length of something, I plus plus, is so common that we'll have a shortcut for it, which is just range list. And this is equivalent to for I colon equals 0, I less than length of list, I plus plus. So that will do the same thing. It will set I equal to 0, and it will carry out everything in the for loop for the entire range over the list. So I will start out at 0, I will then be 1, I will then be 2, and it will do this for every value of I up to length of list minus 1, and then the for loop will stop continuing to iterate, and will eventually return m after that for loop finishes. All right. So we also have another variant of this. So I can quickly grab list of I with a second kind of variable here as part of the ranging. So if I say for I colon equal range of list, I'm going to get I ranging from 0 up to length of list. If I instead do I comma value colon equal range of list, then val is going to give me the values in the list. So at any given stage, val is going to be equal to list of I. So I don't need to check list of I greater than m. I could have a quicker check of just val greater than m, and I'm going to set m equal to val. You don't have to use this. If you like one way versus the other, it's fine, but it just goes to show you that you can use either form. Okay. We could write a sum function as well. We could write a function that, say, takes an array or a slice of integers or a slice of float 64s, and it's going to produce the sum of the values in the slice. So let's say sum takes a slice of integers and returns the sum of values in the slice. And we might apply what we just learned. So we would say something like var sint, or s colon equal to 0, and that's what we're eventually going to return. And we're going to say, well, what do I need to do? I need to range over everything in the slice and add all the values to the slice. Here I don't actually care at all about the index. Before I needed to check whether the index was equal to 0. But for this problem, I just need to range over all the values in the slice and add each value that we find. So I could say something like for I, or we'll use j just for the sake of being different, and value for the sake of having a different variable name, colon equal range over, I called my input slice A. And here I care about adding the values to S, so I know that I want to add value to S. And the other thing we learned about last time is that this is a common notation where we set a variable equal to itself plus something else. And so instead I'm just going to say S plus equals value. So we range over the slice and we add each subsequent value to S, and then we eventually return S. We will, however, encounter an issue here. So if I were to save this and compile it, and now I've got I'm going to still run my program from outside of Atom, but I've got Go Plus working, and I may as well use its built-in compiler feature to check my work as I go. And I'll get this compiler error, which is j declared and not used. So the issue here is that I've declared this variable j that I've wanted to use for indexing over the array, or over the slice, but instead I never actually used it. So it's the same thing that we've seen before when we started working with variables. If we introduce a variable, Go wants us to use it. There's a quick workaround here, which is to just use underscore to indicate that I don't actually I don't need this variable. And now when we save it, Go will be fine with that, and I'm simply ranging over the values of A. Again, there's nothing wrong with doing for I colon equal range of A and S plus equal A of I. Or for I colon equal 0, I less than the length of A, I plus plus. That's fine as well, but these types of shorthands will make our programming, or our coding, I should say, a little easier to read and a little more straightforward to write. So the blank identifier will be helpful. We can also pass, say, a slice as an argument to a function. So, and as a reminder of how this built-in compiler is working, that is in the Go Plus package, where we'll get, where when we save files, we get kind of a built-in compiler at the bottom. But there's nothing wrong, of course, with, if we save things, coming outside, CDing into our directory where everything is stored. You see here it's go src, and we're in the arrays directory, and building, and getting something that compiles that way, and then we can run, although I don't have anything really to run. So passing a slice as a parameter or an argument is also possible. And so for example, say I write a function called, I could say change first one, and I'm going to take a list that's a slice of integers, and I'm just going to update list of 0 to be equal to 1. And there's a good point here too, is I can use underscore anytime I'm not really interested in whatever variable that I'm working with. We'll see that here in a second with respect to in other contexts soon. So here's a function that changes the first element in a list, not an exciting function, but the list is a slice of integers. And here's a function which is change first one, I'll call it array. And this is a very specific function that takes only arrays of length 3 and does the same thing, sets the 0th element equal to 1. It doesn't return anything. It simply takes an array or a slice accordingly and changes the 0th element to be equal to 1. Okay? So I could come into main, where I've got more on arrays and slices, and just to illustrate the difference between these functions, I could, for example, have A is a slice of integers of length 3, and B is, let's say var B is an array of length 3. Okay. And in each of these cases, I get 3 zeros, so they look similar. I have a slice of length 3, I have an array of length 3. Remember that an array has to have a constant length when we pass into it, so I'm not able to change that. I'm not able to give it a variable either. Typically in practice, we'll work with slices more. But I provided this example so that I could call each of these two functions that I wrote. I'm going to call change first one slice and change first one array. And so change first one array, I'm going to call that on B. And change first one slice, I'm going to call that on A. So I'm not returning anything at these functions, I'm just passing them in. And now if I were to print A and print B, we might ask, what is it that's going to happen? And so if we come out to our console, compile, and now run arrays, then two things will be printed. The slice A after passing it into this function, and the array B after passing it into this function. And you'll notice that in one case, the case of the slice, we actually changed that 0th value of the slice. In the case of the array, we did not change the value of the slice, or of the array, the 0th value. So what we've seen before is that when you pass a variable into a function, you typically will create a copy of that variable with the same value, and then that copy has a scope that lasts from the beginning of the function to the end of the function, and then it's discarded. So if you want the value that's stored in anything that changes in that variable, you need to return something. Here, we see for the first time an example of something that can be passed into a function and that the function will have access over that data structure. So in the cases of arrays, we do not have list is a copy of whatever we call function on. in the case of slices, we can edit a slice from within a function. And that's the first lesson to learn. So this will actually be very helpful in our work, but it's something we should be aware of, that we're not copying the entire slice when we pass it into a function. This is actually really nice. It's very memory efficient. So we don't have to create duplicates if we're working with long arrays, for example. We can simply have one array and it can be passed around as a slice through different functions. But we should understand the difference here. Okay. So one more thing I would note is that there is a built-in operation on slices that will come up very frequently, and that will resolve our issue with producing a list of prime numbers. And I will say much more, I should say, on slices and arrays and what's really going on behind the scenes, but I'll provide that as kind of foreshadowing of what we'll discuss when we get really much deeper into how Go manages memory, or how a programming language in general might manage memory, in a few weeks' time. For now, I'd like to come back to our idea for prime finding and say that, remember, we did not know how long to make the length of our slice at the start of our list primes function. And so this will allow us to motivate an append operation. And I've already got a slice of length 3. And so let me append to a value. So here, I know that a is 1, 0, 0. The notation for appending to a slice is append, lowercase. It takes the name of the slice and whatever you're appending to it, and then you update a to be equal to it. Okay. Another thing that I'll say in the future is why the notation is this way. Why not simply append A5, for example, or A equals append 5, or something like that. This notation will make a lot of sense when we understand more about what's going on behind the scenes. There's no need to do so now. So A equals append A5, this adds element 5 to the right side of our slice. And so now if I print A, and I want to run my program, and someone has pointed out I can call go run main.go, and that will compile and run my code for me. I like doing this as 2 steps. So I'm old-fashioned, but I like go build and then // or just calling the executable file name on Windows of whatever the folder is. It's also more natural to work with when you start having like 30 Go files in one folder. Go run of a single file won't behave as naturally as compiling and then running. Okay, so if we look at our run our code, then here we can see that 5 has been appended to the right side of our slice. So all is good there. And I'll say more on append later, but for now I'll point out that this is very helpful with the function that we wanted to write for prime finding. So a natural thing to do is, so that I don't need a prime number theorem or something very mathematically advanced, I'm going to comment out my list primes function. Remember, it takes an integer n, it's going to produce a slice of integers where that slice just stores all the prime numbers. And now I know what I can do. I could have it set to be an initial length, but if I don't know, this is great if you don't know eventual length of primes. So I'm going to just have it have initial length 0. And every time I encounter a prime number, I'm going to append to primes. So the first thing I should do is leverage the Sib-Veritosthenes code that we wrote before, where I know that if I can get a prime Boolean array, something like prime Booleans, is equal to, let's call the Sib-Veritosthenes, and now we're going to see again the power of leveraging subroutines. We don't need to reinvent the wheel here. This will give me an array, slice. I use the term array and slice interchangeably often. It gives me a slice of Boolean variables whose pth element is true if p is prime. And that's nice because now I can use what I've learned about ranging, and I can simply say, why don't I let p range over this slice of Booleans? And every time I encounter a prime, append it to my list of primes. So I can simply say, if it's the case that, and here I could use the same notation, p, comma, prime might be a little awkward. It's really like prime question mark. Let's say is prime. So if the number I find is indeed prime, so I could use this notation. Another thing I could do would be to say prime Booleans of p here. And that's automatically going to check whether or not it's true. If I wanted to be ultra precise, I could test whether or not it's equal to true. So there's multiple ways of doing this. So if that's true, what did I say I was going to do? I'm going to take primes, and I'm going to append to it the p that we found. So we found a prime number, great, and then I'm going to append that prime number that we found to the list, or to the slice. And then at the end, I need to remember to return my slice. So this function calls civ Veritasthenes, and I should be able to call it. So if I were to say, let's not make n too large, but n colon equal to something like 31, and let's call list primes of n. And now that's only going, before I had all these true and false values, now that's just going to give me all the primes up to and including 31. And now we're going to be able to say, well, why don't we just print the primes? And so now when I go build and run my arrays, I have 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and 31 is indeed prime. So I haven't missed anything there. I did manage to capture 31. If I call it on 30, I shouldn't be picking up 31. So I could run my code again. And I don't pick up 31 this time. And so we have really what we wanted, which is a prime finding algorithm. And leveraging kind of the prime Boolean being true or false, we can get any list of primes that we like. Okay? And we know that this is fast, which we saw last time when we timed civ Veritasthenes and saw that even if you plug a value of n that's quite large, it will still be at the millisecond scale in running this. So that's all I wanted to say for now about arrays. And in the last lecture on bacterial replication origins, we started working with strings. And I'd like to cover kind of how Go implements strings and how we're going to work with them here. So that's enough for me on arrays. I'm going to create a new file. And I'm going to save this as, let's put it in a Go src, and I'm going to have a strings directory. Call it main.go. I could call it anything.go. And so everything gets colored nicely for us, and I'm going to print strings. And because I've got the packages behind the scenes that will automatically import FMT for me, if I'm just a little lazy and didn't want to have to type that out. So if we were to, for example, let's say we print string of our favorite letter, A. Now that's going to behave exactly how we would imagine it to behave. Last time when we worked with variables, we saw you can convert from one variable to another. If we have two integers and we need to divide them as decimals, we can simply call float64 of the two integers and divide them. It doesn't change the underlying type, it just locally will change the types to produce, if we want 3/2 to be 1.5 instead of 1. So calling string of a symbol is going to behave the way that you would hope it would. In my terminal window, I'm still in the arrays folder, so I need to go up a level. So I'm going to cd ... That takes me up to the src folder. Now I need to jump down into the strings folder. And we are going to compile what we have. And I'm going to run strings. And so nothing surprising here. I've printed string of A, and that is the string A. Things get a little weird if I tried to print string of 45. You might guess that this will print the string 45. Another trick is that if I want to execute a command in the terminal, I can just hit the up key, and that gives me whatever I typed previously. If I hit it again, it'll give me 2 ago. So I can just hit up, and that gives me /strings. I thought I was going to print 45, but instead I printed a hyphen. And the reason why is that Go is thinking that by converting this integer to a string, Go thinks we want kind of the 45th symbol according to ASCII chart. And you don't need to know that chart, but there's a chart behind the scenes. So when Go sees a symbol, it actually views that symbol as an integer. We've seen that but previously, where I printed a symbol and we saw that Go was thinking about it as an integer. The same thing is happening here. When we tell it 45, then it will actually think that that is the symbol in the ASCII chart corresponding to the integer 45, and so when we take string of it, it's going to produce whatever that symbol in the chart is. Makes sense. Not the most natural to work with always, and unfortunately you need to use kind of a separate package if you want to make these kind of everyday conversions back and forth from different types involving strings. So I always mention it first. There's a package called stringconvert, strconv, and so for example, if I instead wanted to convert to a string, I'm going to call this whatever string variable that I like, and I want to convert from an integer to a string of 45. Now if I print this is going to give me the string 45. And I'll demonstrate that. Go run main.go. So now we print 45. Okay. If we want to go the other way, then say we want to convert, I don't know, the string 37 to an integer. So I want to set j equal to string convert, and now the built-in function is a to I, and let's say it's 37. There's one problem there, which is that things would get weird if I gave it something that wasn't truly an integer. I tried to convert, so another way of seeing this would be var jint. I declare j to be an integer, and then I try to convert hi to an integer, and there's no natural way that we would convert just a regular string that doesn't contain that doesn't contain digits to a string, to an integer, excuse me. And so instead, in this case, if we were going to try to convert this string, this function will return 2 variables, or 2 values. It will return an attempt to convert it, and then the second thing that it will produce for us is an error variable type. And so there are a lot of things that we will do where Go may try to do something for us, and then if it fails, it will produce an error variable of error type that is not equal to nil. So if this goes okay, then error will equal nil, and we can continue on. So if error wasn't equal to nil, then there was a problem. And so we should probably panic or provide some other error message, error, issue converting string to an integer. And I'm going to hit up, go run main.go. I get that J is declared a not used, so let's try and print it. Make sure that everything went well. And now we see that that conversion went fine. If I had instead tried to convert high to an integer, I'm going to hit my panic statement and see that there was an error in converting a string to an integer. So I managed to catch that error, which is good. So be very important that we handle this. If I just weren't concerned at all, then, and I didn't have this error checking, I could always use underscore. Not the best thing to do, because then in this case, and so I wouldn't have any of this code if error not equal to nil, but I wouldn't have my error checking, so it's always good to have an error variable type there, or error variable there. There's another one which is something like if we were going to convert, and this is just a good one to know, if we were going to convert, say, x, and I need a different variable name, say error2, and let's try to string convert a decimal like 3.14, and I need to tell it 64, so this will become clearer later, but it tells us how, excuse me, it's not parse float 64, it's parse float. This tells us how much memory to allocate for the decimal that we produce. Not an important detail at this point in time, but it's important to know kind of this is the syntax that we use. And then I'm just going to copy my code here and say if error2 is not equal to nil, then we're going to panic and produce this error message where there's an issue converting the string to a float. If everything goes fine, we're going to print x. So I'm going to go run main.go. I never changed this back to 37. Give it negative 37. And it's fine with negative numbers too, 3.14, converting this decimal string into an integer. So everything's okay there. I would recall that string concatenation is represented by plus. Okay, so if I wanted to say, running out of variable names, but let's say s colon equals to I, and t colon equal to lovers, and then I were to print s plus t, just as a review, we'll see that when we go run main.go, the last thing that we'll see printed is the string where hi and lovers got glued together. And so we could, set another variable equal to, say, x, or let's say u colon equal to s plus t, and the same thing will happen when I print. Okay, so I can use that concatenation operator. It comes up all over the place, and I've mentioned it last time, but I thought worth reminding you of. Strings are going to work like arrays in many ways. So for example, if I were to print not u, but say u of 0, or u of, let me say, what's the last symbol in u? That'd be length of u minus 1. Remember that we index a string or an array from 0 up to the length of the string or array minus 1. So let's see what gets printed here. These are going to be the last two things that we print. And so, maybe I didn't save. So the last two things that we print are 72 and 115, which are not what we might think of as the final symbols, or the first and last symbols of high levers, but that are the symbols H and S as represented in Go. If I wanted to print whatever they actually are as strings and see them that way, I would just need that little type change there. And now I'll see the H and then the lowercase s. It's a little awkward, for sure, but it is what it is. One last thing I would say, if, say, t of 2 is equal to the symbol v, that's how we would check. So if we had a string and I wanted to check, is that symbol at index 2 of this string t equal to v, then I'll print something like success. And so the last thing we'll see printed is success, because this is in fact true. It doesn't necessarily have to be true, of course, but we'll see that success. Okay. So I want to bring this back to something that we worked on before with respect to bacterial genomes. And so we started working with these DNA strings. And one of the fundamental facts that we learned about DNA strings, or strands of DNA, I should say, is that you have one strand that runs in one direction, and you have a complementary strand that runs in the other direction. So A is always going to bind with T, G is always going to bond with C, and the strings are reverse complements of each other. So we don't read them in the same direction. Because of the biochemistry, the directionality of this string is opposite in the other. And so we had this problem where I wanted to take one strand of DNA and then produce its reverse complement. So what is it? If I were reading the other strand in the correct direction, I would be changing the A's to the T's and the G's to the C's and C's to G's and T's to A's, but I would also be reversing the string. And we saw an example of how calling subroutines can be powerful, because we can start with, let me go and write some functions down here. I said if I were being as lazy as I could be, and I were going to reverse complement some string, let's call it DNA, and I'll say reverse complement takes a DNA string and returns its reverse complement corresponding to an opposing strand. So this is going to take a strand and return a string. And my very allegedly lazy code was to split this into two pieces. Was to first take the complement of every corresponding position in the DNA, and at the end, just simply reverse that. And that's a strong way of programming, because the shorter our functions, the easier they're going to be to write and to debug. Anytime you can split a task into two simpler tasks, we're going to be better off. And so it's just a matter of writing each of those separate functions now, as opposed to thinking about both of these simultaneously. It's actually not the optimal way of doing it. The optimal way of doing it is to start at the end of the string and start building a string by doing both of these processes at once. But I think that for the sake of readability, understandability, and for building up ways of thinking about how we're going to build more complicated programs where we're going to have functions calling each other all the time, subroutines flying everywhere, this is a very strong way of programming and planning our code by splitting one task into smaller tasks. So let's write each of these functions, and just like with arrays, we're going to have a range keyword that's going to allow us to range over a string. So what we would like would be to write a complement function, and I'm going to save the comment because we can think of what we're doing is that we're taking a string of DNA And I should also protect against all cases where, say, a user tries to plug in something that isn't a strand of DNA, so it doesn't have just A's, C's, G's, and T's, it has a random Q in it, or a random number, or some other symbol. But I want to focus just on the kind of problem-solving aspect of this. And so I'm going to take a string and return a string. And this, again, will not reverse the string, but it will find the complementary nucleotide at each position. And so I could range over my strand of DNA. And what I would like to do would be to say, well, of course I need to, let me do this. At the end, I'm going to return DNA. And I would like to just edit DNA as we go. So because strings will be passed in and a copy is created, this will be fine because it's fine to edit the string as we go. I'm going to use this as an excuse for a switch statement. So a switch statement will be a slightly kind of simpler version of saying if, else if, else if, else if, else if. So if we have a lot of else ifs and we just want to divide all our cases up into n buckets, then we can switch based off of the value of DNA of I. So how this will work is it will check what is DNA of I, and it's going to split it into cases. Is it the case that DNA of I is equal to the symbol A? If that's the case, then let's update DNA of I to be equal to T. Let's update, if I get a T, let's update DNA of I to be equal to A. Let's update, if I see a C, DNA of I is equal to G. And if I see a G, I'm going to update DNA of I to be equal to its complementary nucleotide. Okay. It was behaving strangely there, but when I save it, I have the built-in code formatting here, and so that will format it appropriately. And so I'm going to switch based on DNA of I, and in each case, I'm going to update DNA to the appropriate value. It would be the same as if DNA of I equals T, then set DNA of I equal to A. If DNA of I, else if DNA of I equals to C, DNA of I equal to the symbol G. If what I'm testing is the same each time, then this switch statement is really nice to use. So every time I'm just checking what the value of DNA of I is. And so that's switch statements in a nutshell. There's just one problem, which is that this won't work. Okay? This idea of ranging over the string and changing symbols, in some languages we're allowed to edit the symbols that we see in a string. In Go, when we declare a string, we can concatenate to it and so on, but we can't change individual symbols. So this would give us an error. We can't change the symbols of a string in Go. You can in certain other languages, so it's good to know kind of what are the quirks of the language that we're working with. And in this case, we're not able to do it. So I'm going to comment this out completely. Let me just use a multi-line comment. And I'm going to write something else. So we're still going to range over DNA. But instead, let me declare a separate string, something like DNA2, and I'm going to start it as the empty string. And I'm going to copy my switch statement. And so I'm still going to switch based off of DNA of I. But this time, I'm going to, if we're at case A, I'm going to instead append to DNA2 plus, and so I'm ranging over the string, and at a given position I'm simply adding whatever the complement of the current nucleotide in DNA is. And so I'm tempted to do that, where I'm appending a symbol to the string. But Go is very strict about types, and it says DNA2 is a string. DNA2 is a string, and if I'm appending, I need to be appending a string to it as well. So I need to make this a string. If I want it even tighter, I can say plus equal t. And so I'm just changing the structure of this so that I'm appending strings each time. This actually becomes quite inefficient if I try to do it on a huge string. And there's a natural workaround for it, but I think it's not the easiest to teach. It's kind of the first case of how we do this. So I may provide details about that later. But for reasonably small strings and what we'll work with, this is a fine function. And so at the end, I shouldn't return DNA. I should return DNA2, since that's the new string that we want to have. Okay. And I could test this too. So I could test and say, let's, in main, let's set a DNA string equal to something like, let's get every possible symbol in there, ACCGAT. And let's print the result of complementing DNA. So I haven't defined reverse yet, so I'm going to get a compiler error there. I'm going to take the reverse of some string S and produce string S. That's more general than the world of DNA. So I didn't call this string DNA, I'm just calling it S. And I'm going to write this later. So the function will be wrong right now, but I'm just going to have it so that Go is happy. And now we check and see, and we need to run more tests here, but I have my initial string of ACCGAT. And if I bring up my window here, its complement should be TGGCTA. So we appear to be on the right track here. And it's just a matter of now writing a reverse function. So I said I'm going to write that later. I mean right now. And I'm going to leave this one to you for a couple minutes. Allow me to take a short break and leave this function to you. So I can say what it does. Reverse takes a string and reverses symbols. So give that a shot if you like over the next couple minutes, and then I'll show the function. So for this reverse function, we're going to have a string s2, and that's what I'm going to return. And then we're going to need to do a range. Let's range over s. And I could do this one of two ways. I could start I at the end of s, so the far right end of s. It's hard for me to do that with my left hand and go left, but the far right of s. And so we would have for I starting at the length of s minus 1, and then we would I minus minus down to 0. Or we could do it this way where we start I is equal to 0 and we range it up to length of s minus 1. I like this way, but the question then becomes s2. I'm going to keep building s2, and I should say, well, what is it that I'm appending to s2? I'm appending something from the end of s. So I'm appending to s2. If I is 0, I would be appending s of n minus 1. Okay, and so really it might be even helpful to just have a quick n co-equal length of s, so I can use n. So if I is 0, I want s of n minus 1. If I is 1, I want s of n minus 2. If I is 2, I want s of n minus 3. If I is 3, I want s of n minus 4. And there's a pattern here, and this is where, honestly, with students, this type of thing is sometimes the biggest barrier, because this type of noticing patterns and so on is often not taught as strongly as it could be. And seeing that how can we write that pattern that we see? What is it that I'm doing each time? It's s of n minus 1 minus I. Okay, and we can see that that pattern, verify that that works, and it's also the benefit of using pencil and paper for this. If that type of thing isn't already natural, to say, well, I is 0, what value do I need to be getting? It's n minus 1, that matches. And then every time I increase I by 1, I want one value smaller in s. So it'd be very tempting to consider our work here done. But remember that this is a byte or a symbol type, and I need to be appending it as a string. And now we should be good to go. So I could test the reverse function just as we could test the complement function. And this is another benefit of being modular, because the more modular your code is, the more divided it is into subroutines, the easier it will be to debug later too, because you don't have everything as one huge blob of code. You have a lot of short functions that you can test individually that are independent of each other. Okay, so let's test, for example, whether or not we get the right thing when we reverse DNA. And so I should get TAG-CCA, which I do. And finally, when we put these two functions together, we should get the reverse complement. And the reverse complement of ACC-GAT would be TAC-GGT. So let's see what happens when we do that. Do we get that? Should be the last line. ATC-GGT. So we're in good shape there. Okay, so we wrote our reverse complement function, which is one of the things that we encountered when we were working with DNA. That's always kind of the standard first function that you want to write when you're working with DNA. We want to do more than that. The next thing that we saw that I would like to come back to is doing something like counting the number of times that a pattern appears in a text, with the view that eventually we would like to solve a problem like what we saw in the last lecture, where I give you a replication origin or any string, any text of a certain, as well as a value k, and you tell me what the most frequent k-mer or string of length k is that occurs as a substring there. What's the substring of length k that occurs in this text of the maximum number of occurrences? And so that will require us to do things like take a string and be able to slide this window down the string, where the window is shorter than the entire length of the string. And so I need to access, say, the substring of a string starting at position 12 of length 8. And I already mentioned what the notation for that would be in pseudocode, and so that's another benefit of discussing this generally, is that we already know that if I have a text and that I can refer to the substring starting at position 12 of length 8 as just text of 12 comma 20, because the higher index minus the lower index will give me the length of the string that I want. And I know that that's going to start at position 12 and run up to, not including position 20, but ending at position 19, and that it has length 8. So we'll continue doing this here. For now, I wouldn't mind to just comment out a lot of the stuff that I've done at the beginning. I can always bring it back online, like a blank slate of some of this stuff that we've written. So I'm not going to comment out the functions, but I'm going to comment out everything that we've done up to now on strings. And if we had a string, so something like I lovers, then the notation for the substring of S, say starting at position 2 of length 3, is, in the pseudocode I gave it as S of 2 comma 5 in Go, and in some other languages it's just going to be S brackets of 2 colon 5. So this is substring of S of length 5 minus 2 equals 3, starting at position 2. If I want a substring that starts at some position and goes up to the end, well, one thing that I could do, I want it to going up to, but not including that position. So if I want everything, I could do 4 colon length of S. That's a little awkward and so common that I want a suffix or something that occurs at the end of the string, that if I don't specify second index, Go assumes we go to end of string. And the same thing for if I don't specify the initial index. So if I want the first 5 symbols, this would give the substring of length 5 as prefix, I should say prefix substring of length 5. And I'll print those statements. Okay. So here's our string hi lovers. The substring of length 3 starting at position 2 is just space LO. S starting at position 4 and going up to the end is just others. And then we have high space low for the substring that's a prefix of length 5. So you see how this notation will be very comfortable to work with. I will note arrays or subarrays and subslices have the same notation. So for example, if I were to make a slice of ints of length, say 6, and I wanted to set some values so that they're not all zeros, for I colon equal to range over A, let's set A of I equal to whatever we like, -2 times I plus 1, just to give it some values. And then what if I were to print A, and then I'm also going to print, I'm going to print A so you can see all the values, but print A of 3 colon 5. Okay, so that's going to be the subarray or the subslice of A, starting at position 3 of length 2. And when I run that, I get a compiler error. And so we see here are our values of A. It has length 6. Those values were set. And then if I want the subarray starting at position 3 of length 2, I'm going to get -5, -7, which is what I got there. All right. So I'll have a little brain teaser here, which is that given a slice A, how could we delete an element at index I? At a given index, I should say. And I'll let you think about that for a second. So if I want to delete in A, I've set those values, and I want to delete the element of that slice at position 2. What might I do? Do I need a separate function? Or can we somehow use what we've done? Index is equal to 2. I'd like to get rid of that element of the slice A at index 2. And so I don't need a special built-in function, although I could write one. With Go, we could just say A equals append. And I'm going to append, I'm going to start with the subslice of A up to and not including position 2. And then to that subslice, so that's the subslice of excuse me, I should use index. So that's gonna range up to but not including index. So if you think index is equal to 4, that's the subslice starting at position 0 of the array of length 4, which is going to be 0, 1, 2, and 3. Okay, it's going to be those indices. So A of brackets :4 would get me just what I want, the first 4 items. And so I can get the first index items with this notation, and then I want everything past A of index. So I'm going to take A of index plus 1, and now I'll have a colon there to say, take everything that's past that position and append it to the start. Just one thing, I want an ellipsis here. And we use the triple dots anytime we want to append multiple items. Okay, so it's because append is what's called a variadic function. So if you're indicating that I'm appending potentially multiple things, it will understand that that's okay. Otherwise, it would have given us a compiler error. I believe there is a runtime. Let's see. Yeah, it's a compiler error. So it checks the types here, and it says, well, this is not a type integer. And if you just tell it 3 dots, it's going to be fine. And that'll be fine. All right. So I've done that delete. Let me verify that it indeed did delete the desired element. So I should be hacking out that -3. And the last thing that prints is that array, 1, -1, -5, -7, -9, which gets rid of it. So we're good. The other thing that's common would be something like replacing the ith element with the jth element. So, for example, if I wanted to, I can look at the array itself. I'm going to reduce the length of the slice by 1, and I'm going to move this -7 here to -1. Okay. So what I'll do is I'll update A of 1 to be equal to A of 3. And then once I've done that, so let's element at index 1 with element at index 3. So I've moved the -7 to this position, and then I'm going to throw out the -7 that we had before, so I can use what I just did, which is append everything up to but not including 3, and everything starting at position 4 onward, triple dots, and then when I print A, I will see that I've achieved the goal that we wanted, which was to move that -7 to the position held by -1 and delete it after we've done so. Okay, so simple operations being used as building blocks to build up other operations is something that we'll see constantly as we move on. For now, I'd like to use what we've done to come back and solve another problem that we saw along the way. So one of the problems that we saw was this reverse complement problem. Another problem was, let's count the number of occurrences of a pattern in a text as a substring. Okay, that was a computational problem. Input, pattern in text. Output, number of times the pattern occurs as a substring. And we even had pseudocode for this. So we had pattern count subroutine, a pseudocode that I presented. And you might, for example, wonder why not use a strings package. So why not set, say, pattern equal to, I don't know, something like ATA, and text is equal to ATA. And from our work, the specific application that we were working with, we wanted to say the pattern occurred twice in text. And many languages will have a built-in, strings, basic string operation package. And that's called the strings package in Go. And so if I wanted to use that, I'd say I don't need to reinvent the wheel. I'm going to just call strings.count of text pattern. I'm going to like writing this as counting the number of patterns in text, so I'm going to give pattern first, but strings.count wants it to be text first and then pattern. I'll need to, of course, add that to my imports, but I saved that in Go. Adam already added that because of the package that I have built in. And so now the last thing I should see is 2, right? We know that there's 2 occurrences, but Go and many other languages that might have this as built in will not consider overlapping occurrences. So we should write our own function. Okay. And we did that before. So if we wanted to count the number of occurrences of a pattern in a text, we had pseudocode to do this. We had a function called countPattern, or countPattern occurrences. And let's switch the order of the parameters here. Count the number of times that pattern occurs in text. You could do it the other way as long as we know which direction they are when we call the function. And it's going to need to take an integer. And I could review the pseudocode, but the idea of it is to set a count variable equal to 0 to eventually return that count variable. Perhaps it would be helpful to set k equal to the length of the pattern and n equal to the length of the text. That will take up a very small amount of runtime, but just having those k and n variables might make things easier to work with. And then we range over all the substrings of text and increment, i.e. add 1 to count if we find a match. So we should have a for loop. And I should point out that it is very, very tempting for problems like this to do something like for I : equal range over the text. And I'm just going to leave that here for now and say that, well, we could range over the entire length of the text, and then we could check. What are we checking? Does the substring of text of length k starting at position I match pattern? And this is something that we've already done, right? We've already discussed in the lecture on finding replication origins what the notation for this should be. Okay, and that's again like why I like doing it, because it's a more general idea than just the language. It gets you comfortable with seeing this substring notation in a language-free context, and then it's just a review now that, oh yeah, that substring of length k starting at position I, it's just text of I to I plus k. So that's at starting position I, and then it has length k, so the final, the second element here is just going to be I plus k to make sure that when you take that difference you get k. And what is it that I'm checking? Well, if that is equal to pattern, so that's a built-in operation where I can check whether two strings are equal, and if that's the case, I'm just going to count plus plus. And at the end I'm going to return count. And yes, I should have some checking here where I'm ensuring that, you know, one thing I might want to make sure of is that pattern has length shorter than text or no bigger than length text, and that I'm not passing in empty strings, these types of things. Although I could pass in an empty pattern, it's just not going to occur anywhere. Although that's actually going to be weird because the length of the pattern will be 0 and so on. So there's all these cases that we want to build out when we're writing code, but it would lengthen the lecture here substantially, so I'll just make a note of things like that. And so if we're solving this problem, I'm checking if the current substring of length k equals pattern. If so, I'm going to increment count, and we should be good to go. Now I noted that there's going to be a mistake, so I've given that away, and you might already see what it is. That if I try to count pattern of patterns in text, and what's nice about some of these packages built into Go is that it will automatically prevent me from doing text pattern because I just hit tab. When it started to suggest that I called count pattern of pattern text, I could just hit the tab and it brings those up. A very common bug is getting two variables of the same type backwards when you call them into a function. And so if we want to call this, now we should get 2. And I said this is not going to go well. End was declared and not used, so I didn't actually use it. But it might be helpful. Okay, I get a runtime error, slice bounds out of range. And this is such a common error. One of the more frequent errors that you'll see in any context is that I have an array or a slice and it went out of range. And so what this means is, for this particular, I tried to refer to something that didn't exist. I tried to refer to an element or a substring or a subarray of something that did not exist. And the problem here is that as I'm ranging over the text, what this is going to allow me to go up to the final position of the text. And so if k is equal to 10, I'm trying to access the substring of the text starting at the final position of length 10. And that's not a substring that actually exists. So this is now out of the bounds of the slice. So I need to make sure that when I'm sliding the window, I go up to the very end and I don't push off the end. Okay? And the way that we handle this is to say, well, sometimes you just can't use for I : equal to range in all contexts. I isn't ranging over the entire text. I is starting at 0. And last time I said, well, how many substrings of length k are there in a string of length n? And we found that there are n minus k plus 1. And that's the kind of thing that will come up very frequently. And it's another example of where everything will eventually kind of boil down to math. And being able to notice these patterns and explicitly describe what they are. And so if I want to do this n minus k plus 1 times, I can just range from 0 up to, but not including, n minus k plus 1. I could go up to and including n minus k, but I like keeping the notation consistent. It's just so natural to go from 0 up to, but not including n minus k plus 1, because then I know I get n minus k plus 1 things. And I don't have to worry about constantly being off by 1, which is something that I know that some programmers will struggle with at the start. So I'm going to range over this, and now the indexing will be correct. So if I get a match, I'm going to increment count, and now when I run my code, I should find that I get a value of 2. And yes, we should test this on a lot of different examples to make sure that we're right. But for now, I'll note that we've kind of written this function, and we're in good shape. There's actually even a more general way of writing this count pattern function, which would be that, well, technically, if I want to count the number of times that a pattern occurs in a text, I could solve a much more general problem of saying, well, what are all the occurrences of it? So what are all the starting indices of this? And I could write this as count pattern 2. And let me show you what I mean. So if I'm thinking as modularly as possible, I could actually just say, I'm going to have a subroutine called starting indices of pattern in text. And that will tell me what the starting positions of any occurrences that we find of pattern in text are. And I'm going to return the length of hits. So I'm just going to solve this more general problem of finding all the starting indices. So starting indices finds all starting positions of pattern in text. And who knows, maybe this more general problem is going to be useful. It's not any more complicated than what we already did. So I could take, say, function starting indices pattern text string, and then I'm going to return, in this case, a list or a slice of integers. It will allow me to practice this notation that we learned earlier, which is that I don't know how many hits there are, so I'm going to make that initial slice have length 0, and that's going to store all the starting positions. Better might be positions. And then at the end, I'm going to return positions. It may just be a slice of length 0, because I may not find anything. In the meantime, I'm going to take this exact same code. I'm just going to show what happens when I copy all of it down from the previous count pattern function that we had. I'm going to have k is equal to length of the pattern, n is equal to length of the text. I'm still going to range over all the substrings, but I'm going to append to the positions if we find a match. So the for loop ranging is the same. Does it match the pattern? And if so, I'm just going to say positions equals append positions. What is it that I'm appending to it? Well, the starting position, which is I. And so it seems like a harder problem, but the code is just as long. And I'm going to have this separate function that just calls that as a subroutine and returns the length of it. All right. So again, the power of modularity, and that this problem seems maybe it's a little more complicated, but it's really no more difficult. Okay, so that's what I wanted to note about strings and substrings, and a little bit about subarrays and so on, and bring that back to a function that we saw before, kind of one of the simpler, two of the simpler string computational problems that we saw. One, reverse complementing a string, and the other, counting the number of occurrences of a pattern in a longer text. The one problem I want to focus on is finding the most frequent patterns in a text. So taking a text and an integer k and figuring out what occurs the most often of length k. This may have more than one answer, as we saw last time, but it's very applicable, of course, to if the text is the replication origin and I want to find what are the interesting hidden messages or things that occur frequently in that replication origin. So this will require me to talk a little about maps, which is what I discussed on the pseudocode level last time. And so I'm going to have a third file, and I'm going to put this into a new folder called maps inside of src, and call it main.go or whatever you like. And let's say this is frequent words and maps. And I need to import FMT as well. Okay. And so we saw one example of a map was where the keys or the indices of your map are strings or words, and the values are the number of times a given word occurs in a text. Another example would be, say you have another table, and the next thing that we're going to work on is we're going to simulate a presidential election from polling data. And so each state may have a percentage for how a given candidate is polling. And so we could have a map whose keys are state names, so strings, and whose values are decimals, polling percentages 0 to 1 for each candidate. So that's a pointer to what we'll do soon, and get an interesting result, I think, for a collection of real data on a US presidential election. For now, though, I'm going to say that maps, in some sense, generalize the concept of a slice. So we had a slice declaration where we said var a slice events, and then I made a to have some length. And I need to use this. And so maps generalize the slice declaration. And so, for example, if I wanted a variable, let's call it polls, and let's say that it's a map of, well, in this case, it's going to be the state names to the polling percentages as decimals. So the type of this variable polls, this is going to be our table or our dictionary or our map, whichever way you like to think about it. It's going to have strings as keys and decimals as values. So this notation says that the type of polls is not a slice, so here the type of A is a slice of integers. The type of polls is a map whose keys are strings and whose values are float 64s. So just like slices, maps need to be made, so you have to initialize them, and we do so with the make keyword, and I need to tell it the same type, which is a map of strings to float 64s. No need to specify length. Go's going to handle all those details behind the scenes, and there's a whole lot to say about what a map is, really, and the mathematical and complicated details that are required to allow us to have something that behaves like a slice, but whose keys can be any variable type. Okay, that's all I'll say on that for now. I'm just going to say, well, say we want to update polls of Pennsylvania, PA, to be equal to whatever the value is at that given time, 0.517. And I can check, take a few others. Polls of NY is 0.789, and polls of Nebraska's split into districts, but 491 or 401, something like that. And polls of Florida, they can never make up their mind, so we'll say 0.500. All right. Of course, there is a shortcut declaration, but I want you to know what the type is of polls. That it's a variable, just like a string or an integer, and that its type is a map of strings to float 64s. Of course, there is a shortcut declaration if we understand this. Polls co-equal to make map of strings float 64s, and you don't need to have two lines in practice. Okay. So what's nice about this is, the map values get assigned directly. In other words, there's no need to append. I don't need a special keyword or something if I want to update things. This behaves, even though I don't have a specified initial length, it behaves as if I've set it to be infinite. So I can add as many elements as I like, and so this in practice makes it very nice to work with. Just as before, I can print the length of polls too, and that will tell me how many values, their key value pairs I've got. So I'm going to cd ... in my terminal. I'm going to navigate down back into the maps directory, and I'm going to go build and /maps. Okay, so this was just my original. Let me comment this out. This is just showing a reminder of the slice notation. So it has length 4. If we're curious what the actual map is, you know, we can compile and run and see that, well, the map takes FL to 0.5, NE to 0.401, NY to 0.789, and PA to 0.517. Notice that that's not the order that I gave the elements of the map in. And you might guess that it's going to produce these in some order. And in this case, maybe it perhaps looks like these are alphabetical order. So maybe this candidate is very unpopular on Mars. Okay. And let's see what happens. Just kind of made that up. And so in this case, yeah, it's still alphabetical. Let's see. 0.43. Doesn't really matter what these are. I'm just playing around to show that you actually, we're getting some nice alphabetization of these keys, but actually this is just a nice convenient example in this one case that in general these values won't be sorted for you. They're going to come out in no particular order that you have control over. Okay, so for this case it worked out okay, but they're not going to be printed, for example, in either alphabetical order necessarily or in the order that you put them in. Delete these. Okay. And let's see. The other thing I would point out would be if we want to get rid of Florida, okay, and say, yeah, they can't make up their mind, let's just saw them off. Before we needed this append keyword that we use, but if I want to get rid of a key or a key value pair in a map, I can simply call delete of whatever the name of the map is and whatever the key of the thing I want to delete is. And so you'll see after I do that, Florida went away. Okay, the next thing I would point out too is that we can loop through maps as well. So just as we had kind of a double index way of ranging over a slice, we can range over a map too. So if I wanted a nicer way of doing this, I could have a for, let's say, state and percentage colon equal range over the poles. And let's print the polling percentage of, comma, state is a string, is, and we need percentage. Okay, so it prints each of these on a separate line. And now you'll see an example of what I was referencing before, is that you might guess that it's ranging through these in the order I put them in, or in alphabetical order, but NY actually occurs before NE, or occurs after NE, and NE occurs after PA, so the order here that they're printed in is not sorted based off of the keys. It's not sorted based off the values, we can see that, and it's not sorted based off of the order that I put the elements in there. And so there are details behind the scenes that are dictating what actually happens, and it can vary computer to computer. But for the sake of this, I'm just going to point out you don't have that control, and you can get the control over it. There's a way around this that's not too complicated of figuring out how is it that I could print the polling percentages of each state in a certain order, alphabetical or whatever order that I like. There's a way of doing that. I'm going to leave that to you as an exercise. And then the next thing I would say is there's going to be map literals too. So there's array and slice literals. So I could declare a variable called a as, or I could a colon equal, let's call it b. I had a different a up there. So an array of length 4, and it's float 64s, and it's 3.1, 0.0, negative 78.93, and 21.322, okay? So this is a way of declaring a short array where I don't have to use the var b brackets 4 float 64 and then set the values one at a time. I can simply create this literal. This is array and slice literals, and something like prime colon equal. Maybe I'm going to append to it later, so it doesn't start off as having any initial length, or this is kind of not changeable. So maybe this array will never be edited, but the primes, I'm going to start them off at 2, 3, 5, 7, 11, and I'll append to those later. Called primes. So there's map literals too. Okay, and the way that we could do that would be to say something like, say we have an electoral votes map, and it needs to be a map of strings to, let's use unts, unsigned integers, since we don't get to use those very often. And this is going to be a map that contains how many votes in the Electoral College a given state has. Okay, and if that U.S. election, presidential election process isn't 100% clear, I'll review that before we actually code this up. But for now, I'll just say each state has a given number of votes in the national election. So PA has 20, and Ohio has 18, and Texas has 38. And Go demands this final comma in case I add more later. So if I tried to remove that comma, I'd get a compiler error. So I'm going to add that back. All right. And then there's one more thing I wanted to say about maps, which is that before I bring this back to finding frequent words, we can pass a map in as a parameter to a function or return it as the output of a function too. And the natural question would be, if I pass a map into a function, do I get access to the map, or is a copy of the map created? So before we saw that if I pass an array into a function, then it copies the entire array, and so I don't really have access to that original array that I passed in. But if I pass a slice in, I get access to the slice, and I'm able to change elements in there. So the natural question would be, well, what happens if I have a function? And currently, none of this code is going to compile because I didn't use any of this stuff. If I wanted to, I could just print the primes electoral votes, just so it won't get angry at me. And say I have a function called boost love, something like that, okay? And it takes we call it dictionary map of strings to ints, and it's not going to return anything. It's just going to set dict of love equal to 100. All right. And so in main, I could say, let's declare some map of strings to ints, and let's set the initial value here to be equal to 0. And now if I call boost love of dict, and I want to print whatever the value is. So dict of love. And let's see what happens. So there's two possibilities. Perhaps a copy of this dictionary was created, in which case that copy was destroyed at the end of the function call, and so everything went away. And I've got a lot of things named the same thing here, so I could call this dict2 if I wanted, just so I'm clear that when this function is called, perhaps a copy called dict is created, and then that value gets updated, and then the copy is destroyed. Or it could be that I'm getting access to the dictionary. So I've set it equal to 0, and when I pass it into the boostLove function, then it's actually going to change that value of love, and that's going to be reflected when I print it. So let's see what happens if I go run main.go. And so the last thing that I see here, I know I've got a lot of print statements, but the last thing that I see here is 100. So this illustrates that the lesson is like slices. We have access to maps if we pass them into functions as parameters. So they behave more like slices in that regard than arrays. I want to come back to an application of using maps, which was finding the frequent words of length k in a longer string called text. And so I want to have a function here actually. In the pseudocode I called it better frequent words because we had an initial approach that was based off of creating arrays, and we saw that there's a faster, shorter, in terms of pseudocode approach that uses a dictionary, and I'll call it frequent words, or we could call it find frequent words if we want to be stylistically consistent, where we're starting function names off with verbs or action verbs. So it's not just frequent words, we're finding frequent words. It's not just patterns, it's counting patterns. So we could find the frequent words in a string called text, and we're looking for the most frequent words of length k. And we're going to produce a slice of strings because we could be getting more than one frequent word of length k. We could have a tie. We could have two k-mers that occur 103 times. So you could review the pseudocode, but how it works is to start with an empty list of strings. So we don't have any frequent patterns at the start, and so we're going to use again this idea of making a slice of strings of length 0. Way down here at the bottom, we will return that list frequent patterns. And we saw that we can use a subroutine here to form a frequency map of text and k. And this will give us a map of k-mers, or strings of length k, in text to their number of occurrences. I will write that separately. I'll just assume that I've got that function written for now. And now I need another subroutine that does, well, let's say max is the max value in the frequency map. So that's a separate subroutine. This grabs the max value in the frequency map. And now we range over the frequency map, looking for what are the strings whose values achieve the maximum. So looking for the strings which are keys in this frequency map, who's achieving the maximum number of values. So again, I haven't written frequency map or max value. I just know what they do. They, what's their input and what's their output. And if we're really thinking computationally, that's how we're going to start thinking about programming in terms of this function has this input and this output, and how do we use it. So I'm going to have a range. So we're going to range over the entire frequency map. So let's say pattern would be the range over frequency map. And really I'm interested in the value too. So I could do my double indexing there. And as I range over it, I'm going to say, well, let's look for if a current value achieves the max. And remember, in the frequency map, there are going to be no duplicates. So every string of length k is going to occur one time, and it's going to be paired with a value that's its number of occurrences in that text that we're looking at. So if the value achieves the maximum, now I know, well, let's append the pattern to the frequent patterns list. And so frequent patterns equals append frequent patterns pattern. And lo and behold, because we've used two subroutines intelligently, and we've used dictionaries or maps where they're appropriate, we really now only need to write those two subroutines. The function is finished. And yes, we could add issues to deal with. What happens if k is set equal to 0? What happens if we give an empty text, or k is bigger than the length of text? These types of things we want to check and ensure that the user can't plug in values that aren't valid for the function that we want to write. But assuming that's the case, again, if we're just focusing on problem solving, the problem is solved. We just have to write each of these two subroutines. I could leave max value to you. If you wanted to stop, for example, and write max value, I will just, in the interest of time, write this max value of a frequency map that maps strings to integers. And I'll point out that, as before, it won't be as straightforward as we might imagine. So I'm taking a map of strings to ints called frequency map as the input, and I'm going to return the max value. So max value takes a map of strings to ints as input and returns the max value in the map. So I want to say m colon equal to 0. At the end, I want to return m. So I've declared my variable that's going to store that maximum value, and at the end, I'm going to return it. In the meantime, it's very natural to say, well, let's do for underscore value ranging over the frequency map, and it's just like a slice. So I say, if that value beats the current value in m, then I'm going to update m to be value. And that's the same issue that I saw at the very beginning. So at the very beginning, I saw, well, technically, if everything in this frequency map is negative, and if we're dealing with counting strings in a text, then everything is going to be non-negative. But perhaps I might use this max value function in a different context where I'm mapping strings to potentially negative integers. And so in that case, I should write something that's able to handle that. And before, though, how we handled this was to do a check, to say if we're at the first element of the array. But the problem here is that if I want to take, I don't have an I, so I can't check that I is equal to 0 because I'm mapping strings to integers. So the keys are strings, not integers. And there's no real sense of what the first pattern is. And this is, again, be a good time to stop and allow you to think about how it is that we circumvent this, because there's no such thing as the first pattern in the frequency map. We've seen already that they're grabbed in an order that we don't necessarily have a lot of control over. There is a workaround for this, though, and the workaround would be to say I can always declare a variable like first time through is equal to true. And now I'm going to say, well, if first time through is equal to true, or value is greater than m. And I don't need this equal true, because that will be assumed if I just put first time through there. It's going to check whether or not it's true. And I'll get in the habit of doing that. So if first time through is true, or value is greater than m, I'm going to update m equal to value. And I need to make sure that I'm not updating it all the time, that I only do this on really the first time through. And so if that's the case, then I should just set first time through equal to false. And now I'm flicking off that first time through switch. So it's only going to be on very briefly. It will only be on the first time first pattern it checks. And so I'm actually not going to need pattern at all. The first time that it checks this, does this check, it's going to be equal to true, and then it's immediately going to switch it to false, and it's never going to be set back to true again. So that will ensure that I'm able to take a map of strings to any old integers and produce the maximum. And again, I should check this with testing it, give it some maps of strings to integers. That would be a great exercise for you to go into main and declare your frequency maps that you like and check max value on them. And I'm just going to point out, I think we're almost done here if we do that, because I've written max value. There's one more subroutine to write, which is that frequency map. And so I need a frequency map function. Maybe I should call it build frequency map, but I think this is clear enough. I'm going to take a text string and a k integer, and I'm going to return a frequency map. So the type that I need is a map of strings to integers. And so we need to declare, I'll call it freak or dict, whatever we like. Let's make our map of strings to integers. And just for the sake of consistency, I'm going to say frequency map takes a string text and an integer k. It returns as output the map of all kmer substrings in text, I should say each kmer substring of text, to its number of occurrences in text, including overlaps. And writing these function comments really helps us get in the habit of thinking in terms of input and output as well. So we'll have function frequency map. It takes a string text, kint, and it returns this frequency map where the keys are kmers and the values are the number of times each kmer occurs. So I've made that frequency map. I'm going to return it at the end. And in the meantime, I need to say, well, why don't we range over all substrings of text? I should say kmer substrings. So for I colon equal, I hate using I every time. For I colon equals, j colon equals 0, j going up to the length of text minus k plus 1, but not including it. So we know we're going to hit length of text minus k plus 1. And then we're going to increase it by 1 each time. And as we range over, we want to check, does frequency of pattern exists? And pattern here will be equal to the current kmer substring, so j to j plus k. Does frequency of pattern exist? Because if it doesn't exist, I want to create it and set it equal to 1. I have not seen that pattern before. If it does exist, I just want to increment it by 1. So we need a way of checking whether or not a key, there is a key in a map. And so here's one way. I could say underscore exists equals freak of pattern. And that underscore is going to be the value of frequency of pattern if there actually is such a value. But I'm not interested in that value for now. I'm just interested in exists. And this will be the way that this could work for an arbitrary map. So exists is a Boolean equal to false if frequency of pattern doesn't exist, and true if it does. And so I can say if exists equals false. There's always more than one way of doing something. Another way of checking if something is false is just to say not exists. Okay. So if frequency of patterns is false, then it does not exist, and I want to set frequency of pattern equal to 1. Else, I want to set frequency of pattern equal to itself plus 1. The shorter way of doing that is to say plus plus. Now, that will always work in any context, but there is a nice shortcut here. So this is method 1. I'm just commenting it out. Method 2 is a shortcut. And that is just to say pattern, frequency of pattern plus plus. That's all I have to do. If frequency of pattern doesn't exist, Go creates it as default value equal to 0 and then adds 1 to it. That's what we want. If it does exist, it adds 1. Either way, that's what we want. And so that's such a common thing that we would be counting. We would be using a map for counting that we don't need to check whether or not something exists if we have this specific case. So all of this code gets compressed down to just frequency of pattern or freq of pattern plus plus. And that's that. So a very short function here for generating a frequency map, and it's going to be useful enough for other problems, not just finding the most frequent patterns, but anytime we have anything related to the number of occurrences of a substring of a given length in a text. And so that's going to contain all of this information about how many times they occur. Yeah, we could test this, for example. We could, or we want to find our frequent words, we should test each of these functions themselves. But I could say text is equal to something that has something that occurs. Let's say, let's make ACG. I think I had another example where ACG and TAT both occurred the max number of times. So let's set this text equal to something like this, where I've hardwired it so that TTT occurs 3 times and ACG occurs 3 times. I don't think there's any other Kamer that occurs 3 times, or really even close. And so if I call find frequent words, text, okay, and I run this, there are my frequent words, ACG and TTT. So you can now go back to what we've done, where I gave you a replication origin, 500 nucleotide window of a bacterial genome, and find the frequent words that we indicated before. So you're seeing this connection of a practical problem where we wanted to look for replication origins or look for hidden messages within a replication origin and apply it to a real data set, which you can find that we have available. The other side of this problem would be, so that was one of the 2 problems that we were interested in. The other one was, how is it that we look for the replication origins to begin with? Can we do this in an automatic, programmatic fashion where we don't have to run experiments? And the answer to that was that we could produce this skew diagram where we just count the number of G's and C's as we range along the text. And then we look for the minimum value. But that sounds a lot like what we've been doing. And so for something like that, I would like to allow you to do that. And apply that to a real data set as well. So I won't do that here today. I'll let you kind of feel empowered to do that on your own. And for now, I'll just call it the end of the lecture here, since we've learned plenty about not only arrays and slices, but also strings, substrings, subslices, and maps as well. So until next time, when we'll look at simulating a presidential election from polling data, I'll let you enjoy yourselves, and I'll sign off. So can't wait to see you soon. We'll see you then.